Hello again. In this video, we are going to practice what we have done in the previous video for the Poisson random variable. So let's just say we are being asked a probability question related to a Poisson random variable, and that is quite complicated to calculate. Let's just say it's quite complicated to calculate with a calculator. In that case, we can use a programming language R to calculate the probability mass values or the cumulative probability values for that random variable as well. So remember, the Poisson random variable was a limiting case of the binomial random variable, and it has the probability mass function defined as e to the power minus lambda times lambda to the power x over x factorial. And this random variable, Poisson random variable, can take any integer value from 0 to infinity, any integer value. It can take any non-negative integer value. Therefore, the probability mass function is defined for all non-negative integers here. So let's just say we are interested in calculating the probability of a Poisson random variable to be equal to 3 when the rate parameter is equal to 1. So let's just say the average number of fire incidents occurring in a certain district is a Poisson random variable with rate parameter being equal to 1. What is the probability that exactly 3 fire incidents will be observed in the following period or following month? So let's just say this one is the average number of fires per month in that district. Okay, and what is the probability of observing 3 fire incidents? Now for that, you are just going to use the Poisson function that calculates the probability mass function for the Poisson random variable. And first you are going to introduce the value in the probability of interest. You are looking for the probability of a random variable being equal to 3. And then you are going to write down the parameter, lambda value. The second argument will be lambda value, and that calculates us the probability mass value of 3 for a Poisson random variable with rate parameter equal to 1. So how about the probability of x being equal to 3 if the parameter is equal to 2? So let's just say on monthly basis, the average number of fire incidents has increased to 2. Still, we have a Poisson random variable, let's just say. Under that assumptions, what is the probability of observing 3 fire incidents? Now you are going to calculate again the probability of x being equal to 3, but this time the rate parameter is changed to 2, and that probability will be approximately equal to 0.18. Finally, let's just say we have a Poisson random variable with rate parameter being equal to 0.75, and we are interested in calculating the probability mass values not just for 0, but also for 1, 2, and 3 in a single comment line. So we need to change the rate parameter to 0.75, and here, instead of writing a single value, we are just going to introduce a vector of integers from 0 to 3, and the probability mass values for all these 4 values will be calculated as such. So there is also a cumulative probability function, cumulative distribution function defined for Poisson random variable, and that is P Poisson. So you see, in the binomial case, the probability mass function and the cumulative distribution function were respectively D binom and P binom. And for Poisson random variable, we have D Poisson and P Poisson. So let's just say we are interested in calculating the probability of a Poisson random variable to be less than or equal to 3 when the lambda parameter is equal to 1. Let's just say the average number of fire incidents per month in a certain district is 1, and it follows Poisson random variable. What is the probability of having the number of fire incidents observed in the following month to be less than or equal to 3? So what is the probability that the number of observed fire incidents to be less than or equal to 3? Now, actually, for that, you need to calculate the probability mass values from 0 to 3, right, with a rate parameter equal to 1, and you need to sum them up. You need to calculate the probability mass values respectively from 0 to 3 and sum them up. But instead, you can directly use the P-Poisson function, and you can write 3 here, which will introduce you the probability of the Poisson random variable to be less than or equal to 3. So it will calculate all probability masses up to this point. Again, with the same parameter, you would exactly get the same value with a shorter comment. Now, how about this one? We have a random variable x, which is Poisson distributed with rate parameter equal to 2. What is the cumulative probabilities at 0, 1, 2, 3, 4, 5, and 6? So actually, we are here trying to calculate the cumulative probabilities at 0, 1, 2. So this means at 0, we will be having only the probability mass value at 0. At 1, we will be having the probability mass values up to 1, which means including 0 and 1. At, for example, 4, the cumulative probability will be calculated, which means we are just calculating the probability mass values up to 4, starting from 0, 1, 2, 3, and 4, and sum them up. So we are trying to calculate the cumulative probability distribution, cumulative distribution function, which will converge to 1 in the end. Now let's do that. Let's do that from 0 to 6. We are interested in calculating the cumulative probability function or the cumulative distribution function for a Poisson random variable with rate parameter 1. So you see at 6, the cumulative probability comes very close to 1. In fact, instead of up to 6, you can continue this to up to 20. So when you reach to 8, 9, 10, and 11 here, at 11, the cumulative probability will be very close to 1. In fact, the probability mass values for the following values will be very small. So if the average number of occurrence is equal to 1, it is very, very less likely for these number of occurrences to be more than 10, actually. Okay, that part of the probability mass function is almost ignorable. Okay, because the cumulative probabilities have almost reached to 1. Even though this Poisson random variable with I'm sorry, by the way, I'm sorry, in the practice here, it says rate parameter 2, and of course we can continue this with 2 as well. So you see this time the convergence will occur around the 14 point. So if the average number of occurrences is equal to 2, it is very, very less likely to observe the number of occurrences per month to be more than 14. Okay, to be more than 14. So the cumulative probabilities reach 1 here. Even though a Poisson random variable can theoretically take any non-negative integers, probabilistically, it is not very likely to observe a very, very large values. Okay. Now let's just solve question 5. It says, let's just say the number of wrong telephone calls to an office is a Poisson random variable with mean 2.6 per day. Okay, so according to this question, if we say that, if we say that x is a Poisson random variable with lambda being equal to 2.6, that is just going to represent the number of telephone calls arriving, number of wrong telephone calls arriving to that office, and the rate parameter is introduced as 2.6. So the question asks here, what is the probability of exactly 2, 3, and 4 wrong calls will be made on the next day? So because it is asking us exact probabilities of being equal to 2, 3, and 4, we will calculate the probability mass function from point 2 to 4 for integers, from 2 to 4, with rate parameter 2.6, and that is just going to be our answer. In the second part, it says with the probability that less than 3 wrong calls will be made on the next day. Less than 3 wrong calls will be made on the next day. So this means in the second part of the question, it asks what is the probability of x being less than 3. So you see, it is not asking us less than or equal to probability. It is asking us less than probability, which means we need to calculate cumulative probability up to point 2. Because if we are considering the values less than 3, these are including 0, 1, and 2 only, not 3. So P plus 2 at 2.6 would suffice the required calculation, right? And finally, in part C, it asks us the probability that more than 3 wrong calls will be made on the next day. So this time it asks us the probability of X being greater than 3. More than 3 wrong calls, which is 1 minus P plus. Of course, we need to write 3 here because 3 is included in the complement event. So in the desired probability here at above, so let me write that again. This probability is equal to 1 minus probability of X being less than or equal to 3, right? And therefore, we need to write 1 minus P plus 3 to 0.6. So the second argument is the rate parameter. By the way, if you write a question mark and P plus, you will be directed to a web page here. And it says in this D plus and P plus function, the first argument is here, the value itself, the second argument is the rate parameter lambda. Okay. You can read the rest of this page to learn further about this Poisson distribution and Poisson random variable, and also the comments, built-in comments in R related to Poisson random variable. All right, final question here. It says, calculate the probability that at least 2, but at most 5 wrong calls will be made on the next day. It is basically asking us this probability. What is the probability that at least 2, but at most 5 wrong calls are made? So the probability of X being between 2 and 5, 2 and 5 are included in this probability as well. So what I'm going to do is I'm just going to calculate the cumulative probability at 5. It's the same rate parameter. And from that, I will subtract the cumulative probability at 1 with the same parameter. That is 0.6835 approximately. All right. So let's just use R again to draw the probability mass function for a Poisson random variable. Let's just say we have a Poisson random variable with rate parameter equal to 2.5, and we would like to draw it for integers from 0 to 12. Of course, theoretically, the probability mass function can continue up to infinity, but practically, the probabilities for such a rate parameter above 12 are just going to be ignorable. Okay, they will be just small, very small, so we can ignore them. So it is just enough to draw this probability mass function from 0 to 12. So I'm just going to do that. I will say that my input vector is integer vector from 0 to 12. And I'm just going to draw a plot diagram, X versus probability mass function of a Poisson random variable, where the input values are from a vector from 0 to 12, and the rate parameter is 2.5. And I would like to change the plot character to 19th character, which is a black dot. And that is my probability mass function here. As you can see, the probability of this random variable to get any value that is greater than 10 is a very, very small probability. In fact, you can also identify these probabilities just by writing this D part. You see these probabilities are very small compared to the other probabilities. Now, in the next part, we have a probability, we have a Poisson random variable with rate parameter being equal to 4. And this time, we would like to draw these Poisson random variables probability mass function from 0 to 20. And what we are going to do is this time we are going to create an integer vector from 0 to 20. And we are going to plot X versus D plus X, where the rate parameter is 4. Again, the plot character is just going to be the 19th character here. And that is the probability mass function for this Poisson random variable. Okay. Now you see for this Poisson random variable, the probability of it to take any value that is greater than 15 is very, very small, converging to 0 very fast here. the main probability masses are observed between 0 and 10. So though theoretically a Poisson random variable can take any non-negative integer, depending on your rate parameter, if the rate parameter is not very large, it cannot probabilistically take very large values as well, okay? The expected value of the Poisson random variable was equal to its rate parameter. So you see the expected value, the average value that this random variable it can take is 4. All right. Now let's just solve this question number 7. It says it's not related to a Poisson random variable. It is related to a hypergeometric random variable this time. It says the audience of a concert consists of 850 female and 1,150 male fans. So the audience consists of 2,000 people here, 2,000 people, 850 of them are female. We select a lucky 10 of these fans randomly for a backstage visit. So randomly, 10 of these fans will be selected. The question is asking us the exact probability of selecting an equal number of fans from each gender. Which means if I choose randomly 10 of these 2,000 people, what is the probability that exactly choosing 5 female and 5 male fans? Okay. Now, for this probability, remember, we write the total number of outcomes of this random experiment in the denominator and the number of outcomes in which we choose 5 male and 5 female in the numerator, and that is formulated by hypergeometric random variable. That is formulated as choose 850 choose 5, then 1,150 choose 5 multiplied with that one is a Cartesian product divided by the total outcome of the experiment, which is choose 2010. Now, first of all, let me calculate choose 2010. Okay. Now, this value is a very, very large number. Practically, it can yield very large errors, even though you are calculating with a computer. Okay. So, calculating this probably with such an idea is not a very good idea, actually. Okay. Because there may be too many approximation errors here. Now, both the numerator and the denominator of this ratio are very large numbers. Therefore, when you divide these two values to each other, there can be quite large calculation errors. Okay, but the main result is this. So 0.22 is the approximate probability for this if we have a different number of genders in this audience. Randomly choosing 10 of them will yield an equal number of genders with 0.22 probability. Now, actually, in our theoretical course, we have said that in a hypergeometric random variable, if the size of the population is very large and also the number of spatial objects and non-spatial objects are very large, in that case, we can apply a binomial approximation to the hypergeometric random variable. So here, when you choose randomly a person, the probability that it will be a female will be approximately equal to 0.425 in the first selection. Now, depending on your first selection, of course, the probability of selecting a second female will change dependently. However, it will not change too much. Why? Because both these 850 and 2000 are comparatively large values. So if you choose, for example, if your first person selected is a female, then the second person will become a female with this probability, because there will be 849 females left and a total of 1,999 people will be left. But if you select a male in the first choice, then that probability of selecting a second person as a female will be very close to that one, actually. Therefore, we will approximately assume that this 0.425 is a constant probability at all times, assuming that we are making a selection with replacement. Okay, We are making a selection with replacement, and then we need to ask this probability. What is the probability of when you select 10 people? What is the probability of exactly 5 of them to be female with replacements? So what we are going to do is we are going to approximate the same probability with a probability mass function of the binomial distribution, and we are looking for 5 successes out of 10, where the success probability is defined as this. And the approximate result for the probability that is exactly calculated here is a good approximation. Actually, it is very close to the above value. All right, so in this last question, we are going to solve a question related to Poisson approximation to binomial. It says in a manufacturing facility that operates 365 days a year, on any day it is likely to have an accident with a probability of 0.02. So there are 365 days in this facility. On any day, the probability of accident is 0.002, independent of any other day, it says. But this probability is very small. Now the question asks, so let me basically let me summarize the fact of this question. If we want to count the number of accidents in a year, or the number of days with an accident in a year, that is just a random variable x, which is binomially distributed with size parameter equal to 365 and success probability equal to 0.002. Where the size parameter is very large, but the success probability is very small, as you can see. Okay, so this is given by the question. It asks us in the first part, calculate the exact probability of having at least 3 days with an accident in the next year. So in the next year, there are 365 days. And it asks us, in part A, it asks us the probability of having at least 3 days with an accident. So what is the probability of x being greater than or equal to 3? At least 3 days, it says. Now that probability is of course equal to the probable 1 minus the probability of x being less than or equal to 2. Because 3 is in the other side, or let me write it like this. That is 1 minus the probability of x being less than or equal to 2. Remember now, this binomial random variable can only take integer values. Therefore, if we are talking about x being less than 3, it means x being less than or equal to 2. Now that is calculated as 1 minus p binom 2 with 365 as success probability, and size parameter, and 0.002 as success probability. And that is our result, actual result. However, if you intend to calculate this value using calculator or your formulations, in that case, you may make quite large numerical errors. Okay, so it is required to use a software at this point. Now, in the second part, it says, calculate the same probability of having at least 3 days with an accident in the next year, but this time use a Poisson approximation to the binomial random variable. Now remember, we say that for a binomial random variable with a large size parameter and small success probability, it can be approximated with another random variable, which is Poisson distributed. And it will have the rate parameter lambda equal to n times p. This time it will be 365 times 0.002. Okay. And then we are just going to answer the same question as in A. But this time we are going to use the approximation. So the same, but with approximation, and we say 1 minus p plus 2, but the rate parameter will be equal to 365 times 0.002. And that value will be, you see, very close to the above value that we have calculated. So this approximation will be quite good. Okay. So that's the end of the practices related to spatial discrete random variables on R. Please study those very well. The studying R and these questions mentioned in this PDF file will also be helpful to understand the theoretical part of this topic perfectly. So see you in the next video.